Good morning. My name is Erik Shilts. I'm part of the advanced analytics team at Opower. And I'd like to talk to you this morning about how we use Hadoop to solve some of our challenging data science problems. And so quickly, what is Opower? Opower is an energy efficiency company that works with utilities to help their consumers reduce their energy use. And so how we do this, I can introduce through a short study. So several years ago, a scientist in California... Excuse me. Several years ago, scientists in California, Dr. Robert Cialdini, got a bunch of grad students together, and he went out and he put door hangers on people's homes. These door hangers had one of three messages. Some called out money, some called out the environment, and some called out citizenship. And so they said, turn off your AC, turn on your fan, it'll save you a lot of money. Or they said, turn off your AC, turn on your fan, it's really good for the environment. Or turn off your AC, turn on the fan, you'll be a good citizen. And so this is a time a lot of rolling blackouts and brownouts. So call citizenship made sense. And so let's take a quick poll, show of hands. Who thinks calls to money were most effective at reducing energy use? Okay, looks like about a third of the room. What about environment? Remember, this is California, so a lot of people care about the environment. So the environment door hangers, who thinks they were more effective? Yeah, this is the one I would have picked too. And so what about citizenship? Selection year, time, this is really top of mind. Yeah, so about another third. In fact, all of these had zero impact on consumption. They were not effective at all. So money, environment, citizenship had no effect. In fact, I lied. There were 4 door hangers. And this 4th door hanger had a very simple but profound impact. It said, turn off your AC, turn on your fan, your neighbors do it. And this very simple positioning of what your neighbors do was actually very effective at getting people to reduce their energy use. It induced a 6% drop in consumption, where calls to money, environment, and citizenship had no effect at all. And so the founders of Opower several years ago, they read this study and they said, aha, this is what we're going to do. We're going to start a software company, and we're going to get people's energy use. We're going to compare them to their neighbors. And by doing that, we're going to be able to save people energy. We're going to save these people money. We're going to give them control over how they use energy. And it's going to solve some of these giant problems that the world faces with climate change. And so this is what Opower does. Opower crunches a ton of data. We provide people insights about how they use energy. And then we compare that to their neighbors. And so in short 5 years, we've grown to over 300 employees. We have over 75 utility partners all across the US and now in several countries. And in this time, we've been able to save 1.5 terawatt hours. And so over 5 years, 1.5 terawatt hours is about the amount that it takes to power a city the size of New Orleans for an entire year. So we've saved that in 5 years, and we're going to save that same amount, another 1.5 terawatt hours, in just over 6 months. So we're saving a ton of energy. We're getting enough energy to power entire cities, and we're doing it just by this very simple comparison, giving people insight into their energy use, and then comparing that to their neighbors. So people just don't have this context of what uses energy and what doesn't use energy. And we do that through data analytics and behavioral science. So how do people know what they use energy? We use data analytics, we provide them insights, and then we send that to them, and this gets them to reduce their energy use voluntarily. And so what is Opower? Opower is this one giant big data problem. We have tons of energy on 50 million households. We'll have reads every month or even every 15 minutes for every single household in a given territory. And so we need to crunch this data to provide people specific insights into how each individual household uses energy, how that compares to their neighbors, and then by doing that, we can get them to reduce their energy use. And so how do we provide this insight? So that's where my team comes in, the advanced analytics team. We provide consumer insights. And those insights give them context and control over how they use energy use. And so typically, when someone receives an energy bill in the past, they'll have a couple of numbers on it. It'll say how much they use, how much you owe, and what are the additional taxes. Compare that to a credit card bill, where you have itemized lists of every single thing that you spend money on. We think people should have that ability to know what's happening with their energy use. They spend a lot of money on it, but they don't really know why. They know it goes up in the winter, it goes up in the summer, But how much? How much of that is heating? How much of that is cooling? How much of that is just being indoors more? These are the type of things that we can help to give people. We do that with machine learning, with signal processing, with predictive modeling. So we use these tools in order to crunch people's energy use and provide them insights. And one type of insight is something like what we show here. So this is one person's energy use over the course of 2 years. We see that as it gets into the winter and into the summer, their energy use spikes, and the amount that it goes up is how much they use on heating or cooling. And so what we can do is we can take someone's energy use like this, correlate it with weather variables, and then figure out exactly how much they're using on heating, exactly how much they're using on cooling. And these are the type of insights that we can then feed back to the people. You use this much on heating, this much on cooling, this is how much your neighbors use. Now they don't just know that they use more or less, they know how much they're using more or less on specific items. And this is really powerful to them. And so how do we do this? We do this through data science. And so if you look up the definition on Wikipedia, data scientists extract meaning. It's a discipline with the goal of extracting meaning from data and creating data products. Now that sounds exactly like what we were just talking about. Extracting meaning from data to give people insights for how they use energy. And so it sounds like data scientists are statisticians. They use machine learning, statistics, pretty charts, and they refer to this pretty awesome book that we look at all the time. But our argue is that data scientists want to extract meaning. But there's a lot of effort that goes into this part. There's a lot of work you have to do just to get there. And so data scientists don't just extract meaning. Data scientists are data mungers. They're just cleaning data. They're bringing data from one place over to another so that they can extract those insights, so that they can use machine learning. And so again, Wikipedia says it's the process of converting data from one form into another for more convenient consumption. And so this is something that's really difficult to do. You need to do a lot of it. You don't just have one stream of data, you can have tens or dozens of streams of data. You need to bring them all to one place, convert them, just so that you can begin that part of using machine learning, using signal processing. And so internally, when we talk about data munging and preparing the data, we call it plumbing. We say data scientists are plumbers because we're always creating pipes, creating tubes, figuring out how we can transform our data so that we can extract meaning. And the thing about plumbing is difficult. If you don't do it right, in the real world, you get water everywhere, you get a mess. And if you don't do it right as a data scientist, you get data everywhere. It becomes a huge mess, it's hard to clean up, and it's hard to do your next job properly. And so there are a lot of problems with plumbing. And these are problems that I've run into. You have data one place, you need to get it somewhere else, so you just hack to get it there. You create a quick little hack to move your data, and you tell yourself, this is temporary, I swear. And you tell all your coworkers, no, this isn't going to last. It lasts a lot longer than you think. And what if you have multiple sources of data? What if you spend a little more time on it, but you have multiple sources, you need to do a lot of transformations, what are you going to do? And the thing about multiple sources is they're really tricky to handle. Yeah, you can get it to work now, but good luck remembering what any of these things do 6 months from now. And when you have all these series of tubes, how do you keep track of it? How do you make sure they work 6 months from now? How do you make sure you can actually extend it and add a new source of data in 6 months? This is really difficult. Then finally, once you get all the way to the end, sometimes it just doesn't work. Sometimes you have to start over. And if you didn't plumb it well, if you didn't do user testing and figure out how you're getting all these data, sometimes you have to go knock down all the walls and rebuild it from scratch, saving yourself no time. But if you do the plumbing right, then you don't have to spend a lot of time getting back to just where you thought you were. And so data science is a discipline of plumbing. It's building all these tubes. It's building all these channels so that you can extract meaning. And so why do I say it's plumbing and not extracting meaning? Well, it's because where we spend most of our time. We conservatively estimate that we spend up to 80% of our time doing this infrastructure and data munging work. That's a lot of time not spent finding insights. And so that other 20% of the time, that's the fun stuff. That's what we typically think about data science. That's the modeling and the charts and creating these algorithms. And as we tell people, algorithms are the easy part. It's not that algorithms are inherently easy or machine learning is inherently easy, but that's the fun stuff. We love to create these charts, create insights, but we can't do that because we have to spend all our time preparing the data and get it where we want it. So how does this work in practice? I'll take you through an example of the type of question we get asked all the time and how we would solve it in the past and how we solve it now. So when we work with utility partners, they have a lot of these program promotions where they offer something, they'll give a coupon, and they want people to use these coupons so that they can get credit for these energy-efficient items. So imagine they have a coupon for electric tankless water heater for 10% off. It's powered by electricity. It's really efficient because it doesn't have to keep water constantly heated. It heats it on demand. But these things are pretty expensive. And so they want to know who should get this promotion? Who will actually use this? And so one thing we could do is just say maximize take-up rate, send it to everyone, create radio spots, create some TV ads, send a mailer to every single person. The thing about that is it's really expensive, so they also need to minimize the marketing costs. So what they want us to do, data science and practice, is identify the likely purchasers. We can't send to everyone, but we want as many people to take it up as possible, so we need to identify the likely ones and target only them. And so in the past, how would we have solved this? Before we had Hadoop, how would we have solved this problem? The way we solve it is exactly the same. We're going to construct a model of likely purchasers and target them. So it doesn't change our model. Having Hadoop or not having Hadoop doesn't change our model. And so if we construct a model, it looks something like this, where we have a bunch of these inputs and then we have a likelihood of purchasing. And I'll walk through this model in detail for you. So first thing is electric heat. Does someone use electric heat to heat their home? Natural gas is a really efficient and cheap way of heating your home. And so if someone has natural gas, they're unlikely to buy an electric water heater. They'll use a gas water heater. So we want to know who heats their home using electricity, and then those people are likely to purchase an electric water heater as well. Similar purchases. So we know a lot of these purchases, people's purchase behavior on these types of items in the past. So if they've bought efficient items, they're more likely to buy this efficient item. Then as we know, neighbor effects are really powerful. So have their neighbors purchased it? Maybe their neighbors have been talking about this great electric water heater that never runs out of hot water. And so if their neighbors bought it, they might be likely to buy it as well. And so we send people all these communications. We send them reports, we send them emails. They may have our thermostat, they may go to our website. And so we want to know how responsive have they been to the things that we've done in the past. And then finally, type a message. When we compare people to their neighbors, we may say you use more or less than your neighbors. And if people use more, they might be willing to make these investments to get their energy use down so that we give them a more favorable comparison in the future. So we have our model. This is all the data we need. Now we need to go get the data. And in the past, we had this set up where we have dozens of servers, we have hundreds of databases, they're all over the place. We have this legacy system where we need to serve up things in real time. And so while this is great for the ability to send people these insights, it's not great for batch analytics. It's not great to bring all these data to one place. And so what we need to do is we need to find the data over in all these databases, and we need to ship it on over to the left to our analytics server. And so let's do that. Let's start the plumbing. Let's create these tubes that we can solve this problem. So first we pipe the utility data. We create a bunch of pipes represented by these arrows, and we send it on over to the analytics server. Now we get some customer interaction data. How have people reacted to things we've done in the past? Then finally we'll pipe some home energy report data. Send on over to the analytics server. So once we have all these data, we're ready to finish our model. We can do it. But wait, there's a problem. We know some of these predictors. We know things about what neighbors have done and what they've purchased. But we don't actually know electric heat very well. And why not? These data are sparse and inaccurate. These data are typically provided by some third-party vendors that go mine public records about what people have in their houses. And so this tends to be inaccurate. We have done some in-home surveys where we found that people have up to 4 heating types in their home. And so it'll say they have fuel oil, they'll have a water heat, they'll have up to 4 types where they use to heat their home. And so this is really inaccurate. And so what we can do is we can do the same thing that we did for purchasers. We can model the presence of electric heat and use that in our model instead of these data that we really can't trust. And so what would that model look like? Probably something like this, where we have weather sensitivity. How sensitive is a consumer's electricity to cold weather? If their usage spikes, then we know that they probably have electric heat when it's cold outside. What is their neighbor's heat type? Heat type is very geographically distributed. Where there's natural gas, there's likely to be a lot of people with natural gas. And where there's heating oil, there tends to be a lot of people with heating oil. So what their neighbors have, that's probably pretty predictive of what they have. Then finally, what's the natural gas price? If natural gas is really expensive, it's less likely that people took this up in the past. So again, we have our model, we get the data, and once we have these data, we can plug it back into our purchase model, and then we'll be done. So here's our plumbing so far. We have a bunch of twos, but it's fairly manageable. But now we have to pipe neighbor heat type, we have to pipe natural gas price. When we send all these data over, now we have all these extra pipes. But now we're ready to model. So we have it, but wait, there's a problem again. We know some of these predictors, but we don't know weather sensitivity. This is harder. This isn't something that people just come to your website and they enter, my weather sensitivity is 5. This is something that we need to look at someone's energy use, look at weather data, and figure this out. And luckily we know how to do this. This is the type of algorithm that we talked about before. We take energy use, we take weather data, and we can figure out how much people are using on heating or cooling. And so we know what our disaggregation algorithm looks like. We just have to get the data and apply it. So again, weather sensitivity looks like some algorithm that we plug in. And we know we need to correlate electric use with weather use. And then we can plug in weather sensitivity, which we plug into our electric heat model, which we plug into our probability of purchase model. So we have all these nested tasks that we need to complete. And so now we have our plumbing so far. Now we need to go get some usage data, figure out how much people are using. We need to go get some thermostat data. We have thermostats that we can use. Now we need to pipe some weather data. And so once we have all these data, we have all these pipes, we need to build it all back up. And if we go much deeper, then we may not get out, because it's starting to feel a little bit like Inception. We're so many levels down, we might not be able to get back out. But I think we have our kick here. So finally, we construct our disaggregation algorithms, and we calculate the sensitivity for all households. So we pipe this through some weather sensitivity algorithm, and then we store those results. So now we have each person's weather sensitivity located somewhere. So now we have it, and we plug that back into electric heat model. And so now we can impute heat type for all households. So we do the same thing we did before. We pipe in this weather sensitivity into our electric heat model. We impute heat type, whether people have electric heat, and we store those results. And so now we know probability of each household having electric heat. Then we can plug this back into our probability of purchase model. So now that we have the data to finish our purchase model, we calculate the likelihood to purchase for everyone, and then we save those results. So we run it through our algorithm, and then we save those results. And now this one file will have the likelihood for each individual customer that they will then purchase it. So we have it, we finished it, we have our result. It took a lot of plumbing, but we finally got there. And so I say data science is plumbing because we had to construct all these tubes. This is what it starts to look like. It starts to look like this mess that maybe you know how to make it work now, but it'll probably be tough to update or to refresh or to redo this model sometime in the future. And so we have our result, and our utility partner is happy because they have it. And then they come back to us and they say, we have a new request. They say, who would buy an efficient pool pump for 10% off? For those of you without pools, pool pumps tend to use a lot of energy, and there are really efficient ones that can cut your electricity bill in a third or a half. And so this is one of those. And so we start to think, yeah, this is an interesting problem. Pools are probably distributed geographically. They might be correlated with income. There are probably neighborhoods with a lot of pools. So this would be an interesting problem to solve. But then we start to remember what it took last time. This is the last model. We had to, what we thought was an easy problem, we had all these nested analyses that we had to figure out. And we had to do all this plumbing. And so instead of immediately starting to solve this new pool pump model, we might start to do a little independent research on other things out there instead of immediately diving back into it. But it gets better. Now we have Hadoop. And this is where things really change. But they don't change in the fact that we need to construct models. It's exactly the same. Our model doesn't change at all. But Hadoop has one key advantage. Now we have integrated data warehousing and data crunching. So all the shipping data around to analyze it and store it elsewhere and construct these pipes, this is all really simple and integrated in Hadoop. And so this is what our Hadoop cluster would look like. Instead of having all these data on these separate servers on hundreds of databases, it's all in one single place. And so while this may be on several servers, to me it looks like it's in a single place and I don't have to worry about it. And so this is really powerful because all the data are there. I don't have to figure out where to go get the data on which server and where to pipe it elsewhere. It's all in one place. And it also has built-in analytical capabilities. It's fully integrated to crunch my data however I want it. And this is a really powerful tool. And it's really powerful when you combine it with having all the data in a single place. And we'll talk about how we get there. But as I said, our model is exactly the same. We don't need to do anything different. We know that we need to figure out heat type, and to do that we need to figure out weather sensitivity. So we end up in the same place where we have all these nested models that we need to build back up. And how do we do that? We're going to fetch them with Hive views. So instead of creating all these CSV files and then piping them all over the place in the old world, we create views. And views are really powerful tools. So Hive is a SQL-like interface to Hadoop. And Hive views are saved queries that you treat like a table. So instead of storing all these data and pulling it and having to refresh it, you create a view. This view is executed on demand whenever you query it, and allows you to set up really complex analyses. Because you don't have to pull data and then use that data somewhere else. You create a view, and then you create another view on top of that view, then you create another view on top of that view. And then instead of having a 10-page long SQL query, you have all these individual table-like statements that you're able to join against. This is really powerful. And the thing about it, it's always fresh data. You never have to refresh it because these views execute whenever you query them. So if you run it 6 months from now, you get the freshest data 6 months from now. If you run it tomorrow, you get the freshest data tomorrow. It's really powerful. And so it'll take a lot longer to execute, but it's always fresh. And it's really simple syntax. Most analysts know SQL, and it looks almost exactly the same. Instead of create table, you create a view. Then this view will execute this select statement on demand. And so views are data on demand. It's fresh data whenever you need it. And it's the data without the storage. You don't have to store all these new updated data each time. You don't have to keep track of when you last updated it. It's all there. It's all ready for you to use. Because what views do is they point at data without storing it. It points at the raw sources. Or it points at other views. You can have views that point at raw sources, then build views on top of that point on these views. Because they're treated like tables, you can build these really complex analyses by linking views on top of views on top of views. So how does this look like in our example? So we set up a view to get our disaggregation data. This view will pull that exact data that we talked about before, the weather data, the usage data, the thermostat data. And then whenever we query this view, we get it all on demand. And so we have our data. We need to calculate the model and store the results. And Hadoop is built to do both. So instead of sending all the data over to a separate server, we're able to integrate the analyses into views. And we do that with Hadoop streaming. Hadoop streaming allows you to integrate with views, and it gives you a lot of power. So this view will run whatever algorithms we come up with on demand. And so we don't need to store our results of our algorithms. They run them whenever we query it. And this is what Hadoop streaming does. Hadoop streaming can calculate anything. You stream data through any script, and as long as that script can take standard input and write to standard output, you can use any language. So you don't have to learn new tools. You don't have to learn new languages. Use whatever you're comfortable with, and just use Hadoop streaming to pipe it through and create whatever analysis you want. So we use R and Java and a little bit of Python, but you can use anything. If you know a language that can write to standard output, you can use it. And that's really powerful. And the way you do this in Hadoop in Hive is with the select transform command. You select data as you would in SQL, then you transform these columns using whatever script you like. And so it's really simple syntax again. You create this view where you select temperature and usage, and then transform it using this weather disaggregation.r script. So you could write this in whatever language you want, but if you use something like R or Python, you can get some really powerful modeling and statistical tools. And so you don't have to rely on whatever functionality is built into Hadoop, because you can extend it infinitely. Whatever you know how to do in another language, you can integrate here. And so again, it's simple syntax to produce any result. I've implemented my disaggregation algorithm in this view. And so now whenever I query that view, I get the latest disaggregation results. If I run it now, I have data through October. If I run it 3 months from now, I'll have data through the end of the year. And so now we know each customer's heat sensitivity. Just like that, we have it. And then we have it on demand. It's always fresh. And now we're ready to model electric heat. So again, we do the exact same thing. We set up separate views that fetch the data, including pointing at the views that we set up to disaggregate heating and cooling. And then again, we implement our electric heat model in whatever language of our choice using Hadoop streaming within a view. And now we have these nested views built on top of each other, where we have all these nested analyses. And it's really easy to maintain and update and add new data sources and to refresh our data. And so now we know each customer's heat type. And so again, we can continue with the original model that we set out to do. So again, we build a third set of views. These views pull the data for our probability of purchase model. And then we set up a separate view to implement whatever algorithm we come up with. And so now we have views on top of views on top of views. And these nested views allow us to construct these really complex analyses. And so again, now to get this list, we run a single query. If I want a new list 6 months from now, I run one query to query this exact same view. And I take advantage of whatever data we've received in the meantime. And so we get more and more powerful analyses. And let's compare this to the old world. We had all this major plumbing. And what happens if we have a new data source? What happens if someone goes into our website and changes their heat type? That should change our models, but it won't unless we refresh all these data all the time, figure out what new sources we have. And so some considerations on the past versus now. So now, refreshing data is a breeze. Every time we query these views, we query the subviews, which query the subviews, which query the subviews. We get all the freshest data all the time. Where before it'd be major plumbing. What about if we have new households that we want to figure out whether they're likely to purchase this? Now it's a single query because it's just pulling from these raw data every single time we pull it. Whereas before, major plumbing figure out where they fit in for all these nested models. Do we have heat type? Do we have disaggregation? How likely are they? What about if we want to add a new data source? Now it's just a couple lines of SQL. All the data are in one place. It's easy to integrate them. Finally, what if we want to build a new model? So use a similar model for a similar purchase for another utility, or a totally separate model like the pool pump. We can take advantage of whatever we know about them using these views. And so Hadoop radically reduces our plumbing. So before, when we had all these extra plumbing efforts that we had to go through, now all we have to do is use Hadoop, and now we don't have to do it. And so when a lot of people talk about big data, they tend to talk about quantity. And so you'll have Facebook or Google or one of these giant websites where they have billions and trillions of clicks. And while we deal with big data where we have a lot of data crunching to do, it's not just about a single type of data source where you have tons of information on it. It's also about variety. So when we have all these hundreds of databases across these dozens of servers, this is a really difficult problem to deal with because each individual database can fit in one MySQL database. When we bring it all together, you can't put it on a single server. You can't bring it all together unless you have some sort of data warehousing techniques like Hadoop. And so you should remember that it doesn't have to be like this. if you have to go through all these hoops, you have to create all these plumbing efforts just to get some insights that you think should be easy, you could stick with this. You could deal with all the plumbing. You could look for a new job. Or you could turn to Hadoop for your big data plumbing. And that's what we've chosen to do. Thank you. My name is Erik Shilts. Happy plumbing. If anyone has questions, you can ask them or find me. Yeah.
So you mentioned you basically reuse the views all the time, so you get original data all the time. Does that mean that it's very light? You have to do that so you can never basically store your video documents somewhere realize the reused materials?
I'm sorry, I couldn't hear the second half of the question. Yeah.
So is the data that lively that it doesn't make sense to store in your media documents and reuse it from the materialized format? Because your burning cycle things.
Yeah, so the question was, if we are rerunning views on top of views, then we have to rerun a bunch of these jobs each time that we want to get some data. So what about materializing some snapshots and then using those as intermediate steps? And that's a great point. We do that, especially when we are in the process of creating these algorithms, so figuring out what works and what data we need. But once we have it set up in place, we'll remove these snapshots so that when we want to refresh it, we don't have to refresh the snapshots. So yeah, we do that, but mainly for the development and not once it's actually we figure out what we need.
So when you started, did you do more of a big bang approach, put in a big Hadoop cluster, try to get all your data in first, or did you start small, bringing data sets as you found them useful?
So the question was, did we do Big Bang where we put in all the data and then work with it, or did we put in things as we needed them? We tried Big Bang, and so this led to some problems because we have some quite large data sets which were somewhat of a pain to get in at first. But we also weren't ready to move a lot of our capabilities over there until we had everything, so that we didn't have to create these separate workflows and figure out what data are where.
I mean, you mentioned analytics and machine learning.
Yeah.
I believe that you don't do machine learning this way. Crunch completely the time. I mean, 50 million learners every single time you make a view. Can you comment on how you organize the learning stuff and how you run machine learning of the infrastructure?
Yeah, so the question is, how did we actually do machine learning when we have all these views and we split up? So you could, one thing that we do is you don't just run machine learning on the raw data, and so you have these views which will then aggregate the data in some way and then apply the machine learning. And so it depends on what task we're trying to solve, but typically the machine learning won't kick in until we've reduced our data set in some way, until it's more manageable.
A second, but I mean, there is a very big problem, I believe, which is clustering similar usage patterns, because it's worthless to run the model on two identical users, for example, because there is the same information there. Did you manage how you can cluster them? Did you work on that? Because this is a big problem, how you can find out if they have similar usage or energy consumption pattern, so to avoid to run 2 times the model on the same thing.
So the question is, how do we look for people with similar patterns? And we do that a couple ways. There are a couple papers out there that talk about clustering time series data by extracting features, and then you cluster on those features. So instead of clustering on each individual time series, which will have huge dimensionality, you extract features by summarizing the time series, the skewness, the distribution of different things, and then cluster on those extracted handful of features. That's how we typically solve clustering for usage patterns. Yes?
How do we convince the organization to get this type of applications?
So the question is, how do we convince our organization to get Hadoop for this type of application? I don't know. We are sort of the secondary user. We have a lot of capabilities that our product needs to handle. And so we have this fantastic dev team that works with Cloudera to set up other tasks, a lot of them using HBase and more performant parts of Hadoop, whereas we are more concerned with the batch tasks, like using Hive. And so because they chose to use Hadoop, we got all these benefits, but we weren't the primary drivers. Yeah.
You have an answer to that question. The easiest thing you do is just grab down a list of somewhere, install it, and show you what they can do.
Okay. Yes.
Can you mention any public data sources that you use to get information?
The public data sources we use. So we correlate our energy savings and try and look at certain things with respect to census data. A lot of the parcel information that we have about people's households and heat type, that's actually public information, but we use third-party providers to get it for us, because you actually have to go down to the public record office and mine through all these data fields. And so we're not willing to do that. It's public data, but we still pay for it. I'm sure there are others. Like, we use EIA data and stuff from the DOE. There may be others, but I can't think of them at the moment.
So I'm assuming that when you're working with different clients, you've got similar data, but maybe it has a different structure, and it's maybe for a different geographic region. So are you setting up like a different cluster for a different client, or is it all kind of on the same cluster? And some of the data you're sharing, like the public data, maybe there's weather data or something, and then you have like partitions, areas where you're actually doing analyses for specific clients or customers?
So the question is, how do we set up our cluster to deal with different utility clients, because they may have similar but distinct data. We actually have, for most of our databases, we have 4 database types, and those databases will be replicated for each single client. And so all the fields are almost exactly the same. So we can actually take all the similar fields, which are the majority of what we need, and we can create these massive tables of every single, of the same table from every single database. And so we actually put everything together. Because we're working internationally, we have some restrictions around what data we can store where. And so those international clusters will have their own sources, but we much prefer to bring everything into one place, because part of the process of launching with a client is figuring out what their data are so that we can store it in a consistent format internally. Yeah.
Consider using map side or reduce side joins as opposed to views?
We haven't looked at that yet. The one thing we like about views and Hive in particular is it's such a small learning curve, so there's enough to learn as it is, that this is where we started, and we're now looking at other things that we can use.
So it seems like there's still some plumbing going on. Are you coming from your original data sources to go directly to Hadoop, or do you still have like internal data warehouses and databases there that you're now pipelining from on a constant basis?
So the question is, how we still have some plumbing to get the data into the cluster, and so how does that work? So we use Scoop to bring in the data from all these legacy databases, and now we're in the transition for some of our data needs, especially for smart meter data, where we have reads every 15 minutes for every single person. We are starting to put that directly into HBase so that it can be performant for our product. So we have sort of these like 2 fields now. One is we scoop things, the other is some things are directly being transferred in.
First of all, second one is very interesting presentation. Secondly, I have a question. You've got the game plumbing, which you really wanted before. When does it come? How do you say what you wanted to change?
So That's a good question. So the question is, how much did we save by switching to this? Because we talked about 80% of our time was spent on plumbing. It hasn't reduced by much, simply because we've had to get all this infrastructure up and figure out what are the optimal ways to use it. It's still a relatively immature technology, so it's not totally bug-free. Things do go wrong, and you need to figure out what are the optimal ways. So it hasn't reduced by much, but what we're finding is that the time that we spend on infrastructure is much better spent. We're much more productive once we finish the infrastructure. We can do a lot more, whereas before we would set up the infrastructure for one task. Now we can reuse it over and over again. So our time spent hasn't gone down, but our productivity has gone way up. Yeah. Yeah, so what are the challenges of running R through Hadoop streaming? So there are a couple. One is you need to figure out what R is, can be a little, it's not the best scripting language, I'll say. And so you lose data types, and you have to figure out what data are coming in and sending out. Some of these things are going away as Hadoop streaming gets better and Hive gets better, but there's definitely a learning curve to move from treating R as a standard input, standard output, versus an interactive R session, which most of us are used to. Yeah.
Have you tried to incorporate unstructured or semi-structured data like XML and just Hive them as a job for that, or use something else?
So I'm sure someone at Opower has run into that, but on the analytics team, we haven't really used XML data or incorporated XML data into Hive. So I think my time is up. If you have more questions, please find me, or feel free to send me an email. Thanks.